Good afternoon. I'm Felicia Chow from the Office of Communications, and we're live here at NASA headquarters. We've got some exciting news on worlds outside of our solar system today. First, we'll have brief presentations from all of our panelists, and then we're going to answer questions from those in the studio, on the phone, and on social media. To ask a question via social media, please use the hashtag AskNASA. Today's participants are Thomas Zurbuchen, Associate Administrator of the Science Mission Directorate at NASA headquarters in Washington. Michael Gillon, astronomer at the University of Liège in Belgium. Sean Carey, manager of NASA's Spitzer Science Center at Caltech IPAC in Pasadena, California. Sarah Seeger, professor of planetary science and physics at Massachusetts Institute of Technology in Cambridge. And Nicole Lewis, astronomer at the Space Telescope Science Institute in Baltimore. And with that, Thomas, can you start us off with what the big news of the day is?
Hey, thanks so much, Felicia. Look, I've been Associate Administrator for the Science Mission Directorate for close to 5 months, and I've just been in awe, and I'm in awe today about both the depth and the breadth of the science that we do here. We're changing people's lives every day, and we enlarge in the space we know. We stretch our imagination, we inspire every day. And today's story is just that. I'm excited to announce today that Dr. Michael Gillon and his team have used our Spitzer Space Telescope to determine that there are actually 7 Earth-sized planets orbiting the nearby TRAPPIST-1 star about 40 light years away. What's more, as you can see in this illustration, is that 3 of these planets, marked in green, are in the habitable zone, where liquid water can pool on the surface. In fact, with the right atmospheric conditions, there could be water on any of these planets. So for the first time, we found as many terrestrial planets around a single star, and that's the first time we have been able to measure, in addition to that, both the masses and the radii of these habitable zone type Earth-sized planets. These planets are among the best of all the planets we know to follow up, to see, for example, with the James Webb Space Telescope that we're going to launch last year, the atmospheres, and also to look at biosignatures if there are any. The discovery gives us a hint that finding a second Earth is not just a matter of if, but when. Scientists believe, actually, that around every star there could be 1 planet. Take 3, take 5, take 7. And you can just imagine how many worlds are out there that have a shot to becoming a habitable ecosystem that we could explore. And what we really have in this story is a major step forward towards answering one of these very questions that are at the heart of so many of our philosophers, of what we're thinking about when we're by ourselves. And that basically is, are we alone out there? We're making a step forward with this, a leap forward, in fact, towards answering that question. And I'm really excited for you to hear about it now.
Thanks, Thomas. So, Michael, can you tell us more about this finding?
Sure. As Thomas mentioned, we used a Spitzer Space Telescope with our ground-based telescope to discover around the same star, not 1, not 2, but 7 Earth-sized planets. And this is the first time that so many Earth-sized planets are found around the same star. Furthermore, with 3 of them in the habitable zone. And the star itself is what is called an ultra-cool dwarf, which is the least massive kind of stars that exist. And these stars are much smaller, much cooler than our Sun. And still, they are very frequent at the scale of our galaxy, more frequent than solar-type stars. And if you look at this illustration, you see the comparison between a basketball and a golf ball. Well, in our case, the basketball would be the Sun, and the golf ball, it would be TRAPPIST-1. So TRAPPIST-1 is much cooler, much smaller than our Sun, and so the planets in its habitable zone are much closer to it, very close to it, with very short orbital periods. And in these graphics, what you can see are the planets which were found around TRAPPIST-1, with the 3 of them which are in the habitable zone, so also called the Goldilocks zones, where liquid water could exist, is the most likely to exist at the surface of a rocky planet. having 3 of these Earth-sized planets in this habitable zone is very promising for the search for life beyond our solar system.
So what can you tell us about these distant planets?
Well, we have measured with Spitzer very, very precisely their sizes. And furthermore, we have, thanks to Spitzer too, preliminary measurements of their masses for 6 of them. And for one of them, our measurement is precise enough to strongly suggest a water-rich composition, which is very exciting because this is one of the planets in the habitable zone. Furthermore, these planets are orbiting so close to the star that they must be, or they are probably, tidally locked, which means they always face the star with the same side, like the moon, to the Earth. And so if you look at this animation, you can see a view of tidally locked planet with a permanent day side and a permanent night side. The TRAPPIST-1 planet could be just like this. Now what is also exciting here about this system is that the planets are so close to each other. If you were on the surface of one of these planets, you would have a wonderful view on the other planets. You wouldn't see them like we see Venus or Mars, like dots of light. But as you can see in the next illustration, you would see them really as we see the moon. You would see worlds with, which are very big. You could see the structures on these worlds. They would be as large as the moon and even larger for some of them. So it would be a wonderful view on these planets.
Thanks, Mikkel. So Sean, can you give us an idea or more context to Discovery and why Spitzer played such a vital role?
Absolutely, Felicia. I'd first like to say that in my opinion, this is the most exciting discovery we've had yet with Spitzer in its almost 14 years of operation. As you can see in the graphic, the initial discovery of the TRAPPIST-1 system was by the TRAPPIST telescope in Chile in 2016. And immediately after that, we started doing intensive follow-up with a lot of ground-based telescopes and more than 20 days of continuous observations with Spitzer. And what we're able to find is that we confirmed 2 of the planets that were found in the initial discovery and then found 5 more planets for a total of 7 planets in the system, which is pretty exciting. Now, TRAPPIST-1 is an ultra-cooled dwarf, and that means that it's much brighter in the infrared, thousands of times brighter in the infrared than in the visible. So it makes it ideal to use Spitzer, which is an infrared telescope, to do the follow-up on this system. And then as you can see in this animation of Spitzer, so Spitzer was launched in 2003, and it was never intended to study exoplanets. So we had to do some clever re-engineering why it's in space still, and it's more than an astronomical unit away from the Earth, so you can't fly out and do anything about it. But we did clever engineering on the ground to allow Spitzer to measure star brightnesses very precisely, 1,000 times more precisely than we had imagined Spitzer would be able to do. And then what we're going to show in the next animation is how what Spitzer sees the planets very similar to the way the Kepler Space Telescope does it. We don't image the individual planets. What we do is the planets pass in front of the star. We see the amount of light that the star is dimmed by when that planet is blocking it. So the dips you see in this animation are the planets going in front of the star, blocking a little bit of the light. The size of the dip tells you the size of the planet. So we can get the size of the planet directly from measuring the dip. Now, when you see the different planets, they keep orbiting around, and every time they transit, you can measure the spacing between the transits, and that tells you about the orbit, the period of the orbit, how long that year is, and for that planet. And then when we know how long it takes for the planet to go around the star, we also know the distance it is from the star, and that also tells us whether or not it's in the habitable zone. Now, the TRAPPIST-1 system and its planets are in an interesting configuration. The planets are all very close together, and their orbits are spaced such that they gravitationally interact with each other. They tug and pull each other as they go flying around, orbiting around their star. And what that does is it changes the timing of the transits a little bit as the planets are tugging each other, so they don't happen as regularly as you would expect without the tug. And with that, measuring those differences, what we're able to do is measure the masses of the planet. So now we have the mass of the planet, the size of the planet, so we can make an estimate of what the density of the planet is. And that's important because that gives us some understanding about what the composition of the planet is. From that, we can tell where the planets are, whether they're rocky, gaseous, or even watery.
Thanks, Sean. So, Nicole, what can you tell us about studying the atmospheres of these planets?
Yeah, so the atmospheres of planets tell us a great deal about the formation and evolution of planets, and also about all of the physical processes that are occurring on the planet's surface and in the air, especially those that might make the planet habitable or actually indicative of hosting life. We can use space-based telescopes today to study the atmospheres of planets using a technique called transmission spectroscopy, which detects the fingerprints of different chemical species in a planet's air, such as water or methane, ozone or oxygen. We're currently using the Hubble Space Telescope to study the planets in the TRAPPIST-1 system to determine if they have hydrogen-helium dominated atmospheres. It's actually great to find out if they don't. That gives us another push forward in having these planets be, in fact, rocky, and also the potential of those planets to support water on their surfaces. Just last year, Hubble actually probed the innermost planets of the TRAPPIST-1 system, TRAPPIST B and C, and found that they didn't have hydrogen-helium dominated atmospheres. So that's just one more step along the path to having these potentially habitable worlds.
So what do we know about the 3 worlds in the habitable zone?
Sure, so I'll use eyes on exoplanets here to give you a brief tour of the habitable zone of the TRAPPIST-1 system. So if we zoom out to the system away from the host star, you'll see all 7 planets, with the habitable zone indicated here in this blue region. The innermost planet in the habitable zone is TRAPPIST-1e. So in this illustration, you'll see an artist's rendition of TRAPPIST-1e, which is a really interesting planet for a number of reasons. It's very close in size to Earth, as you can see here. It also receives about the same amount of light as Earth does in our own solar system. This means that in TRAPPIST-1e, you could have temperatures that are very, very similar to the ones that we have here on Earth. The next planet out is TRAPPIST-1f. Now this is a potentially water-rich world that is, again, about the same size as Earth. You can see here in comparison. Now TRAPPIST-1f has about a 9-day orbit, and during that time it receives about the same amount of sunlight as Mars does in our own solar system. And the final planet in the habitable zone of the TRAPPIST-1 system is TRAPPIST-1g. Now TRAPPIST-1g is the largest planet in the TRAPPIST-1 system. It's about 13% larger radius than that of Earth, as you can see in this comparison here. And it receives about the same amount of starlight as somewhere in between Mars and the asteroid belt in our own solar system.
So while we don't have the technology yet to really travel to any of these planets, how long would it take to travel here?
Well, thankfully, we can ask eyes on exoplanets. And if we were able to travel at light speed, we, of course, could arrive in 39 years. Something more like a jet plane would take far longer, of course, something more on the line of 44 million years.
Wow. Well then, thank you so much, Nicole. Now, Sarah, why are these discoveries so exciting for the scientific community?
Well, with this discovery, we've made a giant accelerated leap forward in the search for habitable worlds and life on other worlds, potentially speaking. Because with not just one planet, but several, we have room that if we didn't have the habitable zone quite right or weren't sure quite what we're looking for, we have many chances over. You could say colloquially, it's like in this planetary system, Goldilocks has many sisters. Now, we don't know much about the planets. We know, as we heard earlier, the masses and sizes and how much radiation is falling on them and their orbits. So for now, we just speculate. And for that, the TRAPPIST-1 system has really captured our imagination, and we have a new travel poster for you that you can download from the NASA website. And if you see here, it's captured scientifically accurately how on one of the planets you could see all the other planets in the sky. Now, historically in exoplanets, in the kind of brief history of the last 20 years, when there's one, there's more. And so that's why I'm so excited to be here today to share it with you, because with this amazing system, we know that there must be many more potentially life-bearing worlds out there just waiting to be found.
Thanks. So what are astronomers doing to learn more about this system and others like it?
Well, first of all, Mikkel and his team have started to put up more telescopes. They call it Speculus, and they're going to, from the ground, use telescopes to search 1,000 of the nearest ultra-cool dwarf stars. And actually, I just have to back up a second about this TRAPPIST system because I forgot to mention that one of the reasons astronomers are so excited about it is it's a veritable laboratory for studying planets orbiting very cool, very small, very dim red stars that are so incredibly different from our sun. In fact, astronomers constantly go back and forth about all the excitement about these worlds because they're very easy to study. Other people have fears and concerns, and so we actually get to test many people's theories about these worlds being tidally locked and radiation from the host star and things like that. So hopefully, we're counting on Speculoos to find more of these systems and planets around these ultra-cool dwarfs, these very common stars that we can study. So in addition to the Speculoos, in astronomy, when someone makes a discovery like this, we put almost any telescope that can follow up to follow up. And so in that way, we have, we heard about Hubble already from Nicole, but the Hubble, Kepler K2, Spitzer, and other telescopes are exploring the TRAPPIST system further. I'd say that what the team is most excited about, although this is still a bit in the future, is the James Webb Space Telescope, which will launch later in 2018. Because with this telescope, and the reason the TRAPPIST planets are so significant is that they are accessible to observations with the James Webb Space Telescope. You can see an animation of it here. So with the James Webb, we'll be able to study the atmospheres, and we will try to assess the greenhouse gas content, which will help us understand the surface temperature of the planets. Are they indeed the right temperature to support liquid water and life as we know it? In fact, we're even going to use the James Webb to search for gases that don't belong that might be produced by life, such as oxygen, ozone, methane, and a whole host of other gases.
Thanks, Sarah. So before we go into Q&A, Thomas, do you have any closing thoughts for us?
You know, for me, this research in exoplanets is really in its gold rush phase. You know, it started something like 20 years ago, and I just couldn't help but notice that the last co-author on your paper is the same co-author who was there at the announcement of the first exoplanet ever discovered and announced in 1995. And since then, we've found thousands of those, a little bit under 5,000 the last time I checked. Dozens of them are in the habitable zone. None until now have had that many planets in the habitable zone. And it's only expanding. This is going forward at a rapid pace, not just because of the telescopes that are there now, but the telescopes we're launching soon. And you talked about the James Webb Telescope, but also TESS, of course, that's going to be there, and WFIRST that's being planned right now. Again, really opening our lens, opening our viewpoints onto the universe, and especially, in many cases, these exoplanets. I do believe that many of the best telescopes that will give us the most information are yet to be invented. There's many things we don't know, many questions we have that come up when we see these observations. We look at all these animations. Very likely, nature is way more beautiful, way more amazing than what we've animated here. It's always that way. And so for us, the question is, how do we actually open up our lens and see these things? How do we get so much data from that the kind of questions that Sarah asked are actually able to be answered? And for me, at the end, it's all about that thought that I have so often when I go to bed at night and really imagine how these other worlds really look like. The fact that there are worlds out there, just like the Earth, that have some commonalities with the Earth, and you could imagine these worlds. It's just only happening right now. These questions about are we alone are being answered as we speak in this decade and the next decades. So I'm really excited about this.
Thanks, Thomas. With that, let's transition to Q&A. We've got a ton of questions on social media, so we'll go there first. If you'd like to ask a question using social media, please use the hashtag AskNASA.
All right, wonderful. We've got lots of questions coming in. This first one comes from Twitter user JJams, who asks, what is the total amount of possibly habitable planets we have found, including these TRAPPIST discoveries?
Okay, I'll take that one. Okay, the total number of habitable planets, believe it or not, is unknown. And it depends on who you ask and how you count them. We would say that there are, let's say, a few dozen exoplanets that you might consider habitable. But the bottom line is that many of them may be a bit too hot or a bit too big. We really have to wait until we can see the atmospheres to know how hot or cold the planets really are. And that's why the TRAPPIST planets are so relevant, because they actually, unlike a lot of the other habitable zone planets, we can actually assess them in the near future.
Wonderful. All right, the next question here comes from Scott, who asks, any confirmation of water on the planetary bodies?
Yeah, I can handle that one. There's has not been any confirmation of water on these planetary bodies. And it'll take a lot of observations with Hubble or in the future with Webb to probe the atmospheres and see if we can detect water on these planets.
But I think it's fair to add that people are looking.
Yes,
and
we
getting
are
lots of
certainly
data on
looking.
Great. This question comes from Twitter user Matthew, who asks, will this be one of the first observations for JWST? And how much can we learn about TRAPPIST, E, F, and G until that mission launches?
I can take that one too. You know, a lot of folks, since learning about the system, have thought about observing it with JWST, and I am fairly certain that cycle 1 will see some observations of almost all of the planets in the system.
And then I guess to add further, even now we're continuing to take observations from the ground and with Spitzer to look at the transit timing variation. So we're going to get better measurements of the masses of these planets as time goes by. And the next year we'll have much better measurements than we have currently.
Okay, we're going to take one question on the phone line from Jay Bennett from Popular Mechanics, and then we're going to go back to social media. So Jay?
Hello, everyone. I was wondering if the fact that TRAPPIST-1 is a particularly cool red dwarf means that it's more likely to support planets that are potentially habitable because it doesn't have as much stellar activity, solar flares, eruptions, these types of things.
I can take this one. So ultra-cool dwarfs are known to be very active when they are young, and this is the main concern about these potentially habitable planets, that they could have been, the atmosphere been eroded strongly by the star when it was young. Now it's quiet. It's a quiet ultra-cool dwarf, so it's not very active. But maybe when it was young, the conditions were quite different. So it will be by observation that we will really figure out the past of this planet and what happened during this very active and young phase.
I'll just add to that and rephrase what Mikhail said to just say the great news is we can observe in the near future. We no longer have to rely on what we think and speculation, because nature usually is smarter than we are. And if there's any way for a life to get a foothold, we like to believe it will.
Thank you. We're going to go back to social media. So Jason?
All right, this question comes from Twitter user Amara, who asks, have you decided any names for these planets yet?
Yeah, definitely.
A name. To give them a name.
Will they mean like a popular name? Like?
Oh, well, we have plenty of possibilities, which are all related to Belgian beers, but we don't think they will become official. So
Right.
For now, let's call them B, C, D, and so on.
Admittedly, we have no way to easily give official names to exoplanets in the same way that we do for asteroids, but perhaps it's something we should try to change.
Great. This next question comes from Twitter user Joe Fiend, who asks, does the Earth-sized planets have any moons revolving around them? And if no, how can there be possible waves on water?
Well, in our data, we have no indication of a moon. And so, furthermore, if we look at our theory, it would be quite unlikely to have a moon around a planet so close to its star. So maybe if there are outer planets still to found, maybe they could have a moon. We'll see in the future. There are still many news to come about the system.
But I'll add further, the tidal forces between the planets are not negligible. So if there was water on these planets, there would be tides as well because of the tidal forces between the planets instead of planet-moon.
Yes, indeed.
Next, we're going to go to the phone lines. We have Keith Cowing from NASA Watch. Keith?
Hi, a question probably best for Sarah Seeger. I'm looking at these planets. I assume they're really close together. It reminds me of the Jovian and the Saturnian systems where stuff is thrown from one world onto another, and there's questions about why, should you consider these as an ecosystem? I'm a biologist. I'm looking at 3 potentially habitable worlds real close to each other. Should we be thinking that conceivably the biosphere around this very tight-knit group of planets might extend beyond just one planet if they're this close to each other?
Well, that's a wonderful question, and we haven't thought that far yet. But I'm sure there's a student out there, listening in who should take this problem on. I'll just back up one step, though, and answer a slightly different question, because if we want to think about an intelligent civilization elsewhere looking back at us, they may be having a press conference saying, hey, there's 3 habitable planets there. Venus, Earth, and Mars may appear to be in the habitable zone no matter how we describe it. So let's wait and see what's out there. But great question, and hopefully somebody will work on this.
Next on the phone lines, we have Marcia Dunn from Associated Press.
Yes, hello. I was wondering, how many years do you think it might take to have a real good handle on the atmospheres of these exoplanets? And I have a follow-up question.
Yeah, so we could actually make a substantial amount of progress in the next, after the launch of JWST, the next sort of 5 years range. So starting with Hubble and then moving into JWST to continue the exploration of these atmospheres, we could see results, in the early 2020s.
And thank you. And I know this is the first time 7 Earth-sized planets have appeared around a star like this. What is the closest runner-up to that? How many Earth-sized planets around a star that you've seen prior?
3.
I think it's a 2 or 3.
Yeah.
No more, found by Kepler.
And which star is that?
Oh, I don't remember. There are so many Kepler planets.
Okay, thank you.
So let's go back to social media. Jason?
All right, this question comes from Miles O'Brien here on Twitter, who asks, what sort of instrument could be used to answer the question of whether these planets harbor life? Could Webb do it?
Sure. So Webb has a suite of instruments that cover, wavelengths from sort of the near infrared all the way through farther into the infrared spectrum. But in particular, it has a lot of very powerful spectrographs aboard. So this is going to allow us to do this transmission spectroscopy technique that I talked about earlier. And it covers the right wavelength range where we can start to detect molecules like water, methane, ozone, and oxygen. So we can start to do a lot of what Sarah had suggested in trying to determine habitability and also the potential of it harboring life.
And I just want to add one thing, and to Miles and everyone out there, is we really try to emphasize we have the capability to find signs of life elsewhere, but nature has to deliver. And because it's all so new to us, these red dwarf stars, we don't totally know what's out there. So if nature has made life ubiquitous, and there are lots of atmospheres without clouds, substantial enough accumulation of gases, we'll have no trouble finding it at all. But if it's the opposite, then it may be a while. But I did want to add one more point that we hadn't covered yet, that we have the TESS mission upcoming, we have other ground-based searches. So TRAPPIST-1, we're just here as the first. It's the most exciting one so far, but we hope to have many more of these and lots of chances to find signs of life in the future.
Wonderful. Next question here comes from Twitter user Chris Sims, who asks, is it possible to listen to this planet system using our SETI-style telescopes? How do we learn as much as possible?
Okay.
To my knowledge, it was already listened to by SETI, and they had no signal from artificial signal detected. So it's doable, but there's no signal detected.
Great. Next question comes from Twitter user Sawyer, who asks, how far into the foreseeable future until we might be able to see a craft that can actually make the journey to TRAPPIST-1?
This is a really hard question, just because it requires so many miracles on the way. See, when James Webb was developed, the way I think about James Webb, it required something like 10 miracles, kind of things we had never done, and kind of put it together into a telescope, with a 6.5 meter kind of foldable mirror and a thermal system that's a tennis court in size. Kind of how do you do that? The answer is you start inventing your way forward. This question that's being asked may be a 100 miracle type of question, and some of them probably relate to nuclear propulsion. Some of these miracles relate to radiation protection. They relate to things that we're just starting to push at. Now, the good news is there's a lot of work that's being done on kind of the first 5 to 10 of those miracles that are being looked at, not necessarily because we have our eyes set right now on going to a star. It's a big leap, but because we're looking, for example, at the outer solar system. We want to get there a lot faster. We want to get there with more payload. We want to get there with more energy. And so the way this game works, it's really, it's leaning forward. It's really, just because it takes 100 miracles, not backing up. That's really what I would believe is what NASA is all about. And that's also what led to this kind of discovery in many ways. Spitzer itself had a whole bunch of miracles on detectors and systems, and the same is true for the other question.
I'd like to just very briefly mention our colleagues at the Breakthrough Foundation and the project called Starshot. And you can go look that up and see that they're planning 19 miracles to figure out a way to send very tiny and thousands of little tiny spacecraft flying by the very nearest stars. That would be Proxima Centauri, not quite like TRAPPIST. But I just want to remind all of you, although it may sound discouraging, perhaps that in our lifetime we won't have a way to see how to get to TRAPPIST-1, that we're here because we have these big sophisticated space telescopes, Hubble, Spitzer, James Webb, and future ones. And we're big on remote sensing. So even though that's what we have to live for, we are still very excited about the possibility of using our telescopes to see what's there, rather than we have to leave the trip there to future generations.
We've got a lot of questions on social media, so we're just going to keep them coming. Jason, what other questions are we getting?
Sure. This next question comes from Twitter user Aku, who asks, any estimations on how old these discovered exoplanets are?
Yeah, the age of the star and the system itself is poorly constrained. We know it's not very young. It doesn't show signs of youngness, so it's at least 500 million years old. But we can't say more because these ultra-cool dwarf stars, they evolve super slowly. Their lifetime is 1,000 times larger than for a sun-like stars. So we don't see them evolving, so we can't constrain their ages.
All right, this next question comes from Facebook Live here. What is the distance between these three planets? Is it something like 500,000 kilometers? And what is the distance between E and the star?
The distance between the planets are a few times the distance between the Earth and the Moon. So we're talking about something like millions of kilometers and not hundreds of millions of kilometers for an Earth around a sun-like star. And for the planet F, the distance is something like 5% the distance between the Earth and the Sun. So it's much, much closer to its star.
Great. This next question comes from Twitter user Ross Butler, who asks, is the TRAPPIST-1 system the closest to us with planets in the habitable zone?
No. In fact, the closest is Proxima Centauri, which has a planet which was detected by radial velocity, so by another method, which doesn't tell us the size nor the mass. So we don't know if it's a rocky planet, but it is in the habitable zone, clearly. It's only at 4 light years away. It's the closest star, in fact.
All right, wonderful. This next question comes from Twitter user Unconventional Tiger, who asks, I would like to know the range of orbital periods for the 7 rocky planets in the TRAPPIST system.
So the range goes from 1.5 days for the innermost planet to, we don't know the period of the outer planet, but it must be something like 20 days. So super short period compared to the Earth.
I think, do you want to add the ratios?
You can add the ratio.
No, I think, Mikhail, you should add the resonance and the integer ratios.
Okay. So indeed, also the periods themselves are related by our common cerebral, so they are related by ratios of integer numbers, which is very peculiar dynamical configuration that we can find in our solar system for the Galilean moon around Jupiter. And it shows that, it indicates at least that these planets should have formed further out and migrated and been trapped during this migration inwards in this very peculiar configuration. If this is the case, they are super water rich because they must have formed in an environment which was very rich in ice or in water ice, and it should be reflected in their composition. And we will know soon, thanks to notably to many new Spitzer observations that are coming.
Okay, before we take more questions from social media, I'd like to ask each of you to kind of give some thoughts about why this finding is so exciting for you personally. And we're going to start with Nicole and then work our way to Thomas.
Yeah, so this finding is really exciting for me because this is a great opportunity to study Earth-sized planets' atmospheres in great detail. We know that we can get good signal-to-noise ratios, and we can start to begin this journey in trying to understand what the air is like around rocky planets outside of our solar system.
Well, I'll give 2 favorite reasons. One is when I and others started in exoplanets 20 years ago, our peers all dismissed the work as just stamp collecting. We'd never look at their atmospheres, we'd never be able to do this, we'd never be able to do that. So the fact that we're here today with 7 planets, and we know we can study their atmospheres in the future, is truly tremendous. The other point I want to make is that we're really excited because we all see ourselves here as just, we're the group of people, we meaning us and all of our colleagues, as the pioneers. This is a search that will go on for many generations. And just the fact that we're this close now to finding so many habitable worlds is really exciting.
Yeah, so for me, it's more of a very kind of a personal experience because I've worked on Spitzer since 2002, and the ability to be able to do these observations. We had to do a fair amount of engineering work, and at the beginning, it wasn't clear necessarily that we would be able to achieve the precisions we need to do science like this. So it's very gratifying that all our hard work, myself, my colleagues at the Spitzer Science Center, JPL and Lockheed Martin, the engineers there, we're able to pull it off, and we're able to give great data to scientists and get great results out. So I'm very happy about this.
So on my side, I've already wondered about the possible existence of life elsewhere since I'm a kid. And so when I went to college to study science, I first studied biology, biochemistry, because I wanted to understand what is life, really. Then I switched to astronomy because it was the beginning of the exoplanet adventure. We were really beginning to detect planets outside the solar system. And it was clear that within a few decades, we would be not detecting giant planets which were unsuitable for life, but planets that could host life, that we could study. So I've already been devoting my time in science to this goal. And then we're getting nearly there with this result. It's a very good satisfaction for me.
To me, looking from the point of view of NASA's science program, it's exciting because it's a leap forward, but it goes in parallel to the other leaps we're taking right now. Look at what's happening at Mars, where we're really looking at the complex chemistry that's happening there. Look at the recognition that Mars actually is a place where there not only used to be water, but there's water today, abundant water. In parallel to that, the recognition that we can now have the technology ability of going to Europa and actually looking at that system, which is in its own right really an exciting system because there's an ocean world there that hits the rock at the bottom in a really unexpected place in a site. There's many other places like that. And then on the theory side, we already heard that the really understanding of the biology of life. There's a tremendous amount of progress. So together, these areas really create kind of a crescendo towards that, really answering that question that has been on our minds for so long. This is the right time to ask that question. It is the right time to have this discovery right now.
Thank you. I'm afraid that's all the time we have left. Please keep those questions coming by sending them at the hashtag AskNASA. And for more information and to download the Eyes on Exoplanets app that Nicole was just using earlier, please go to nasa.gov/exoplanets. And also, don't forget to follow us on our various social media